So today what I'm going to do, guys, is I'm going to talk about, well, I'll go over one example, which is an important example. There are a couple of things in that example that I want to make sure that you know how to deal with when you see in a problem or in some specific situation. And then briefly, I'll talk, well, not exactly briefly, but I'll talk about Tracker, the software that we are going to use for or projects. Like I would say 3 or 4, I believe 3 or 5 projects you're going to do during the semester, excluding the final project. You need Tracker, so it's good to spend a little bit of time in a class, go over some of the features and things you need to know to be able to navigate the software and get what you want out of it. So let's, before I get started, I wanted to mention one thing that I briefly looked at your homework assignment submissions, like first homework assignment. I just had a comment about the homework assignments. And that comment is about the plots, right? The graphs that, or plots you made with the graph software. First thing I want to mention is that if you're comfortable with MATLAB or any other plotting software, I'm not forcing you to use graph. My idea or my logic for this course is that I don't expect you to know any coding. So in order to get the graphs and plots that we want, I am introducing, or I introduced graph. I made some tutorials on how to use the graph. And if you don't know coding and you don't want to deal with coding, since it's not part of the requirement for this course, I expect you to use graph to plot. So whenever I ask you to plot something, it means you have to use the graph software or use your own software, whatever you have for plotting. Handwritten plots are not acceptable. You can't just draw a plot by hand and say this is the plot. When I tell you to plot something, that plot has to be drawn with the software. Preferred software is graph because, as I said, that's what I introduced, and I expect you to be able to use that. The second thing is when you provide a graph, guys, have some sense of when you look at that graph, try to make it better. There are some graphs there that, for instance, if I want to, let me see if I can. There are some graphs there that, x-axis is this way, let's say y-axis is this way. And then you have a graph that somehow you plotted up to here, and then you provided this whole thing as your submission. And all these empty space here, I don't know what is it doing there, right? So make it, fit the graph to the window, make sure the thickness of the line is proper, labelings are good, the font size that you use for different things, labels and legends, are good when you put it in your homework assignment or submissions, your homework submission or your reports for your projects, right? There are things that, spend few minutes on the graph. That's all I'm asking. Right? Just wanted to mention that. So whether or not I say use the graph, when I tell you to plot something for the rest of the semester, you have to plot that function, whatever data that is, either using graph or use a software that you know, for instance, MATLAB. If you have issues with that, just send me an email. We can set up a meeting and we can just go over how to use graph to plot that specific function or set of data that you'll get later on during the course. Okay, I just wanted to mention that. Now let's, so last class, well, last week, or better to say all the classes before, we talked about 2 vibrating systems. One was a spring mass system. The first one was a pendulum. We looked at pendulum as the simplest oscillating system. And then we talked about spring mass system. And we said how mathematically they are the same. They are different systems, but what happens is that differential equation governing the motions of these two systems are the same. So we don't have to solve this second order differential equation again and get system response, amplitude, time period, natural frequency, or different things about the system. We could just make a comparison between these two systems and say, well, if this was this for the pendulum, I can just replace G with this and L with this and then get the system response, this time in linear motion, for a linear motion. Now, what I want to do in this one example that I'm going over today is that what happens if we have a mix, right? So spring mass system is a translational system and a pendulum is a rotational system, if you remember. Now, what happens if we have something of a mix? What happens if we have a system that has springs in it and also has some kind of a rotational motion, right, in that system? How do we deal with that? So I'm going to add a couple of, like, better to say, some kind of curveball I'm going to throw at you. And in this example, well, pretty much throwing at myself because I'm going to solve the example. Hopefully that helps to clarify some concepts as well as some procedure that you will understand why we solve the differential equation and what happens if we have different types of system. Are we going to solve the differential equation again whenever we use Newton's law and write equation of motion? Or can we use whatever we learned from before to get what we want, to get the system response and properties of the system, right, such as natural frequency and time period? So let's take a look at this example. Let me put it here, example. So we have let me use this. So we have a bar, uniform bar, something like this. It is rotating around the point O. I'll just call that point O. There is one spring attached to the end of this bar, so end point, with the stiffness K2, and another spring somewhere here, K1, called stiffness K1. What I'm asked to do in this example, to find the natural frequency, find the natural frequency and system response to the given initial conditions, for, this is important, for a small rotation about point O. I call that rotation theta. So a couple of properties of the system, or the numbers that we need. This, let me complete this. So this is L over 3. This is L over 3. I didn't do a good job scaling, but they all have the same length, or the distance is the same. The length of this bar, or sorry, mass. The mass of the bar is 2 kilograms. The length, or L, the value of L is 3 meters. K1 is equal to K2, and that's 100 Newton per meter. And also, as I mentioned there, I am given the initial conditions, which are the conditions related to rotation about point O. So the initial displacement, initial velocity. initial displacement is 1 radian. Just it's rotated 1 radian, and initial velocity is 0. So no initial velocity is given to the system. Well, it's we let it go after we rotate or move it for 1 radians. So I think that's pretty much everything we need. Okay, so how do we solve this, right? This is kind of a mix of, we have springs, we have something that's rotating around the point, and this time this is a bar. We are given the mass of the bar, so this is not even just a pendulum. Now, as I said, the same thing that we did before. First, we have to assume some direction for this motion. It's either rotating clockwise or counterclockwise. I'll go with clockwise, but whatever I do holds true, or whatever I say here is true if you choose to go with counterclockwise. So I do what I did before. I have to start from free body diagram, right? I need to draw a free body diagram and then kinetic diagram, or inertial forces, and then find the equation of motion there, find the differential equation that's governing the motion of the system, and see how things go from there. So let's draw this again. And I'm just going to use a straight line to make my life a little easier. And let's say I'm assuming that it's rotating clockwise, and I'm exaggerating a little bit. So obviously the theta is more than 1 radian. So this is 0.0. This would be my free body diagram. And the equivalent of it, I'll draw another one for kinetic diagram. This is 0.0. These two should be equivalent. I'll just use let me use equal. So looking at free body diagram, what do I have there? Or what do I expect to have? Kinetic. There's one thing I have to add to this problem statement. Motion starts from equilibrium. Very important thing, that this assumption that is going to make our life much easier. So what forces do I have on free body diagram? Any thought on that?
You have the springs.
Springs, right? So I have to have some force applied from the springs. Now the question is, well, obviously one spring forces, one of them will be applied on this bar somewhere here, right, where it's attached to, and the other one is applied at the end of this bar. Now the question is, since I'm assuming that, let me draw a horizontal bar line here, and this is theta. Since I'm assuming that it's going downward, that's the direction of the motion, what direction should I use for the forces applied by the spring? So I know the one force is applied here, let's say where the first spring is attached to the bar, and another force is applied, let's say here. I'm going to put it at the top. Now, what is the direction of these forces? How do I know which, should they be upward or downward? Should they push the bar upward, or they should pull it down on my free body diagram?
They push it upwards, because that's where the static equilibrium point is.
Very good. Yes, exactly. That was the point I was trying to make. So everywhere in this course, whenever a system is disturbed from its equilibrium position, right? This is motion starts from equilibrium. The springs or the spring forces, the main thing they do or they want to do is to push the system back to where they were. So any deviation from equilibrium point, springs forces are going to be in a direction in a way that they're trying to push the system back to the equilibrium position. So in this case, they're going to be upward because they want to push it back to where it was, so assuming that the horizontal line is the equilibrium position. Before I go further with the spring, are there other forces on this bar?
Reaction force to the support.
Yeah, I have reaction forces, right? For those, I'll just put them just right there and there. You'll see they're not that important the way we're going to analyze the system. But to make sure that free body diagram is complete. Now, well, this one I'll call it, assuming that this is X, and this is Y, my coordinate system. I'll call this OY, I'll call this OX. Let's go back to the springs. Well, these springs, we decide about the direction. We said, well, we know force is a vector, so we have to decide about their magnitude. We know the spring force is stiffness multiplied by the amount that the spring is stretched or compressed. Now we know the stiffness, right? This one is K1, this one is K2. We have to find how much is the deformation in each spring from equilibrium point, right? The green line, the dotted line, the green dotted line is says equilibrium point. To do that, right? So what is the deflection? The deflection is this amount for this spring, and is this amount for this spring, right? The bar is going down. In this case, I decided about the direction. So this is how much the spring is compressed. Well, K1 is compressed, K2 is stretched. Now to find that, I'm going to look at the geometry. Right? Use a little bit of trigonometry there. This length, well, I know this length is L over 3. This one is L over 3. And this is also L, sorry, these are not actually L over, yeah, these are L over 3. That's the distance between where the spring is and the point that the rotation is carrying around. Let me see if I can use a different color so things are less confusing. So now, this length and this length, and also these two black lengths, I actually don't know. I'm just gonna call these, like use some parameters to, let's see, some around about X direction. So I'll call this X1, and then let me go from the beginning. And I'll call this X2. Let's see if I use the same notation. Yeah. For these, I'll call this Y1 and Y2. I don't know what those values are yet. I'm just using letters to identify them. Now, theta is the coordinate that I care about, and I want to write everything based on theta. Right? Theta is the rotation. It's the only thing that is happening. One coordinate that I need to describe this motion. But now I have Y1, Y2, you know, which are they? Okay, let me complete this. These are the values that the spring is stretched, right? So I can just add them to here. So this spring force, I guess at this point it's better if I use green so the spring is more clear, is going to be K2, Y2, and this spring force is going to be K1, Y1. Y1 is the amount that the spring 1 is stretched, Y2 is the amount that the spring 2 is, if spring 1 is compressed, the spring 2 is stretched. Y2 is the amount the spring 2 is stretched. So I want to write everything based on theta, not y1 and y2. I don't know what those values are. I just put those names there so I can identify these forces in springs. So to do that, my goal, keep in mind, is to write everything as a function of theta. So let's see what we have. For y1, if you look at this triangle here, let me draw it here. This is point O, so this triangle there. I know this is L3, L over 3. This is y1, this is x1, and this is theta, and this is point O. So looking at this triangle, so right triangle, right, what's the definition of cosine? Or let's go with, I guess sine is better. Sine theta. Right? We'll use both. Just find sine and cosine theta in this triangle. We'll see where am I going with this. Sine theta would be the opposite, y1 over L over 3. And cosine theta would be adjacent, which is x1 over L over 3. So this means that y1 becomes L over 3 sine theta, and x1 becomes, you'll see why I'm finding x1. Right? Maybe I shouldn't have mentioned it, and I should have mentioned first why we need that. But for now, just trust me and come along. So L over 3 cosine theta. So I could write y1 and x1. y1, you know why I want it. x1, you'll see why, because when I want to find the moments about point O, I have to multiply the force and the distance that force has from the point of rotation, which is x1. And I don't want x1 or y1 on my equation. I want to write everything based on theta. So y1 becomes L over 3 sine theta, and x1 becomes L over 3 cosine theta. Oh, I wrote both of them as a function of theta. This is good. That's what I wanted. For the second spring, the same thing. I want to write the amount of deflection I have in the spring as a function of theta, and the distance that the spring force has from the rotation, because at the end I'm going to use the rotational version of Newton's law. The summation of all moments about point O is equal to mass moment of inertia times angular acceleration. I'm going to use that. To do that, I need to know the distance the force has to the point of rotation as a function of theta. So to do that, well, I'll follow the similar procedure. Right? This time, look at this triangle. If this is point O and this is theta, look at this triangle or the geometry, x2, y2, and this would be 2L over 3. Right? That's the distance from O to the end of this bar. So you can just follow the same procedure, same logic, writing sine and cosine. You'll get y2 would be 2L over 3 sine theta, and x2 2L over 3 cosine theta. Okay, let's keep these here. Right? So I could write some geometrical parameters based on theta that I wanted, which was what I wanted. So I'm just going to keep these here, separate them. This is what I wanted to achieve, what I wanted to do, and I achieved that goal. Now let's go back to our free body diagram and kinetic diagram. Well, first, what is missing from kinetic diagram? If I'm looking at a rotation, right, a rotation around point O, well, keep in mind, I said, well, the rotation is clockwise. So I'll just add I-O, whatever the mass moment of inertia of this bar is around point O, times angular acceleration alpha. Right? Oh, in this course, we just represent the velocity and acceleration as time derivatives. Right? We represent them with theta dot and theta double dot instead of omega and alpha. So I'll just put I-O theta double dot, which is the same as I-O alpha. Now let's try to write the equation or form the equation of motion. Summation of moments around point O should be equal to I-O alpha or theta double dot. Now, rotation is happening in counterclockwise, and I said in this course, always take the direction of the rotation as positive. So here is the positive direction. Let's see what we get. Look at the free body diagram, which is pretty crowded at this point. I'm going to start with writing the equation in terms of x1 and y1 and x1, y2, and then we replace those values we got there. So the first one is k1, y1, the force. Well, OX and OY do not do anything. I'm taking moment around point O, about point O. So OX and OY are out. K1, Y1 is the force multiplied by the distance of the force from point O. Now you see why I found X1, which is X1. Now in terms of direction, right, it's counterclockwise. The moment it creates around point O. So I'll put a negative here, minus, because I took clockwise as the positive direction. The second force is the second spring. It's going to be K2, Y2, and the distance it has from the point of rotation, which is point O, is X2. And this one is also counterclockwise. So this also will be negative. Is equal to mass moment of inertia of this bar around point O, theta double dot. Let's just leave it as IO theta double dot. Then we'll deal with it later. Now let's start plugging in the values we have. Well, minus K1, Y1, I wrote it as L over 3 sine theta. So I put it here, L over 3 sine theta. X1 is L over 3 cosine theta minus K2, keep plugging in, Y2 is 2L over 3 sine theta and 2L over 3 cosine theta. This is equal to IO theta double dot. So technically, if you do this math, this is going to give you the equation of motion for this system. Now, keep in mind, there was a small but important assumption that was made there. Here, I don't know why I have similar colors multiple times. I said for a small rotation about point O, and that's the hint. Tells you, well, small rotation, meaning that you remember what we did for a pendulum. We said when a pendulum is swinging, well, we ended up having sine theta in our equation, and then we went through this whole process of how can we simplify this equation and linearize it. We said, well, this gives us a second order differential equation that is nonlinear. How can we linearize it? We said, well, for a small rotation, remember I draw that unit circle, I said sine theta for small rotation is equal to theta and cosine theta is equal to 1 when the rotation is small. We look at the unit circle and we basically made that, we draw that logic from there. So I'll do the same thing here. This is a nonlinear differential equation. If you do the multiplication, you have theta double dot. That's good. You can take everything to the right side, and then you're going to have some second order differential equation, but it has both sine and cosine in it, which is nonlinear, and we can't solve. So I'm going to linearize this. By linearizing, I mean pretty much replacing sine theta with theta and cosine theta with 1. Linearized, meaning that sine theta for a small theta is equal to theta, and cosine theta for a small theta is equal to 1. If you do that, then look what we had here. We had L over 3 sine theta, which gives us L over 3 theta. L over 3 cosine theta becomes L over 3. So this becomes minus K L over 3 squared times theta. So the minus K1 L over 3 squared theta. This comes from the first term. The second term, Well, 2L over 3, sine theta is replaced with theta, cosine theta is replaced with 1, so minus K2, 2L over 3 squared times theta, so it becomes minus K2, 2L over 3 squared times theta. So how small things or how simple things are becoming by just making one assumption that this rotation is small. Remember, I said as long as theta is smaller than 10 degrees, that's a very safe assumption to make. Go above 10 degrees, the farther you get away from small angles, more error you're putting into your equations, and the system response you get compared to what happens in reality if you do that experiment. So you're making an assumption that's limiting the capabilities, your capability in solving this problem. And the other side is just IO theta double dot is equal to IO theta double dot. Now we're getting somewhere more familiar. So if I move things around, I keep this on this side, and I say, well, let's take these two to the other side, factor out theta, and let's see what we get there. K1 L over 3 squared plus K2 2L over 3 squared, theta is equal to 0. This becomes the linearized version of the equation of motion, right? Equation of motion, parentheses, linearized. Now look how, or at least to me, familiar this is. This is very similar to the equation of motion we get to for a pendulum and for a spring mass. If you look at this part, this is pretty much just something times, oh, maybe I should use circle, something times theta double dot plus something times theta is equal to 0. It's the same form of the equation of motion. So we don't need to solve this again. We're in a situation that we have the differential equation that is perfectly familiar, it's totally familiar, and we have the solution to that differential equation from before. All we got to do is the same thing as spring mass, right? It was the second derivative of whatever coordinate we were using, something multiplied, plus something multiplied by the coordinate that we were using. So this was for pendulum, this was for spring mass. Compare these two with what we got. Pretty much the same thing. So what we do is that whenever we study a system, we derive the equation of motion as long as there are only mass, there is only some mass rotating or moving with some spring, you always end up with an equation in this form. So now you see why we spend time and solve the equation of motion for some simple pendulum and a spring mass. Because everything else falls into this category. You can derive the equation of motion. Sometimes you have to make assumptions like linearizing the equation, but you end up with the same form of differential equation. So this, well, in this equation, right, that's what we do. We say, well, looking at this, I have the equivalent of mass, M equivalent, which is IO, and I have the equivalent of a stiffness. What is the equivalent of a stiffness? Whatever we have behind theta. So that would be the whole coefficient, K1 L over 3 squared plus K2 2L over 3 squared. That's pretty much it. The rest is whatever we know from before. If I continue this, well, let's start making things a little simple. I know K1 is equal to K2, they are the same, so let's just call both of them K. I'll plug the numbers at the end. But let's say K1 and K2 are the same value, so let's just call them K. I can simplify this. This becomes K comes out, then we have L squared over 9 plus 4L squared over 9, which becomes 5 K, well, let me write it this way, keep the K out. 5 L squared over 9K. So I have equivalent of mass, equivalent of stiffness. What I'm asked to find? I'm asked to find natural frequency first and system response. So natural frequency, what was natural frequency? Omega n is the square root of whatever is the stiffness of the system over whatever is the mass of the system. So in this case, the stiffness is K equivalent. The mass is M equivalent. Does this make sense, guys? This is what we do over and over. You'll see in other systems, we solve this equation of motion for a simplest form of the system. And then from there, whenever we're dealing with a system, as long as we can derive the equation of motion using whatever energy method or Newton's law, we just use what we found from before. So I just plug in square root of K equivalent is 5 L squared K, and I'll take the 9 down, 9 I O. So this is my natural frequency for this system. Now, about that IO, mass moment of inertia about 0.0. We got to do something about that too. Right? We are not given this value. We are given the mass, the bar, the length of the bar, and where everything is with respect to that point rotating, the bar rotating around it. Now, going back to dynamics, as I said in the first class, the way I look at vibrations is it's kind of applied dynamics. You're using a lot of concepts you learn in dynamics to be able to study the systems, vibrating systems. We go further, but we still use a lot of what we learned from before. Let's see, what is the mass moment of inertia? Let's see if anyone remembers. What is the mass moment of inertia of a bar? Let me put it here. Mass moment of inertia. Let's just start with this. We have a bar and it's rotating around its center. Its length is L. Its length is L, let me see. And its mass is M. Try it as a bar. What is the mass moment of inertia for this bar rotating around its center? I'll show it with I bar, meaning that mass moment of inertia around center of mass. Assuming it's a uniform bar, it's rotating around its center of mass, which is at the center. Does anyone remember that? Can anyone remember that? Or can you tell me what it was? Well, we really...
For a bar, it's 1/12 the width times the height to the third power.
Well, you are talking about area moment of inertia now. I'm talking about mass moment of inertia. All right. Area moment of inertia is well, concepts are the same, but mass moment of inertia, what we use in dynamics, area moment of inertia mainly use probably when you're studying solid mechanics. So the mass moment of inertia, 1/12 is right, is on point.
Is it 1/12 ml squared?
Yes, exactly, Michael. M L squared. Now, this is for a bar. You don't need to memorize this. Obviously, I'll give this to you. I just want to refresh your memory about how things work. Now, this is a bar that it's rotating around a point that is not at the center. Right? If this is point O, and this is the center of gravity, right? We have a distance, D. Right? This bar is not rotating around its center of gravity, O. It's rotating around its center of gravity in the middle. It's rotating around point O, which is different from its center of gravity. Right? So what is the mass moment of inertia for this? IO. If you remember, we were using parallel axis theorem. We were saying that, well, I bar whatever we had for mass moment inertia around center of gravity plus md squared. And d was the distance of the point that the rotation was occurring around it from center of gravity. So keep that in this corner just as a reminder. So we're going to use that knowledge. Right? We're going to find IO. So knowing this, what is IO for us in this case? Well, we have 1/12 ml squared. We're given the mass and the length of the bar. Plus, what do we get? We have m times d squared. What is d here? What is d here? If, let's say, center of gravity is somewhere here, in the middle of the bar, and it's L/2 away from this side, this is d. Right? What is the value of d? I'll go ahead and tell you, which you'll see, you'll agree, but d would be just L/2 minus L/3. Right? This is L/2 from this end to here. L/3 is the distance from the end to the point. So d is L/2 minus L/3. Right? Hopefully you agree with me. Stop me if you disagree. L/2 minus L/3 squared. So IO becomes, if you do this math here, it's going to be L/6, L squared over 36, 3, 4, would be 1/9 ml squared. This is IO. And I'm going to plug this back to what I had. So that becomes, well, 9 times 1/9, get rid of that, ml squared, L squared, L squared, is simplified, so can be simplified 5k over m. This becomes the natural frequency of the system. Natural frequency of the system. Want to find the value, just plug in the numbers. Square root of 5 times k was 100, divided by mass was 2 kilogram, so it becomes a square root of 250, whatever the value is. Let me see if I have the value. It's about 15.8 radian per second. It's natural frequency of the system. Next, now we have to find, oops, going back, some reason I zoomed in. Let me see if I can fix it. I should be able to do it. Don't give up on me yet, guys. Almost there. Okay. Now, next, we have to find a system response. System response to a given initial condition. So the rest is hopefully straightforward to find the system response. So system response would be theta t is equal to a sine omega nt plus phi. So I have to find a and phi. Well, a would be square root of, where is that? Theta naught squared omega n squared plus theta naught dot squared divided by omega n, and phi would be tan inverse theta naught omega n over theta naught dot. So going back, we know theta naught is 1. Theta naught dot, initial velocity, is 0. Right? So this goes away, and this is 1. Let's use that. This becomes omega n over omega n. This becomes 1. Remember, it's a radian, the unit for amplitude, because it's a rotating system. And phi, well, theta naught is 0. Something divided by 0 is infinity. And think about that unit circle. This becomes pi over 2. So once you have this, you can write the system response. Theta t is equal to A is 1, so sine square root of 250 t plus pi over 2. And that would be your system response. There you go. So we got both the system response and natural frequency for a system. We could find time period, obviously, from natural frequency. That's what we were asked to do. So the key was to write everything based on one coordinate, which in this case was theta, and use trigonometry from before. That's what we did to write that, to fulfill that requirement, writing everything based on one variable. And we linearized the system from there. Another important point was that we got an equation of motion that is very similar to what we had from before. Any question about this, guys?
Professor, can you go back to the page with system response?
Last page, yeah. Did I make a mistake there?
Thank you.
Okay. So I have about half an hour less than that. I'll use that to go over quickly the tracker, the software, because I'm going to announce the first project. Well, I'm going to post the first project today, and it has 2 weeks to submit. And you need to use Tracker to be able to get the responses or the answers for that project. So I already put a couple of videos on Moodle. I'm hoping you already looked at those videos. Let me bring it up. Move things around. Right. If I can extend this to fit it in this frame. Just, you know, guys, I also put the information for the TA for the course, his Charles. You can contact him. I put his office hours and link to contact, his email. Feel free to contact him with whatever concern you have, if any question about the course. So if I'm contacting me, you can also contact him and talk to him. He's a pretty, he was a student of mine, and he's a pretty good student. He's a very good student. Now, if you scroll down all the way at the bottom, I put a link for Tracker. I'll click on that. It takes you to the software page, or maybe not. Display. Oh, I forgot that you actually have to click on. And you can just install the software. Right? Depending on what operating system you're using, just click on it and follow the procedures. Procedure is pretty much a bunch of next. And I put some videos. These are tutorials made by the developer of the software. So they give you very good, thorough information about the software and how to use it. Now, I just want to do a little bit of review, right, about general procedure that you probably need to follow for your projects and anything else that you, when you're using this software for video analysis. The idea is that I give you videos of experiments because we can't really do experiments. And I want you to do analysis, get the results from experiment, and in so many cases, compare that with the analytical solution we got. So if you open the software, this is pretty much the first page you're going to get. Right? If this page is not there and this tab is closed and you get something like this, you can always go to File, New Tab, and this page is going to come up. Now, first thing you do, you open the video. Open file. I have 2 videos here. Let me see how many of them I can get through. Yo-yo desk is some video that is pretty much someone is letting a yo-yo go, and I want to measure the displacement and the velocity of this yo-yo going from the top to bottom. Now, a couple of steps you need to follow when you open the video. First, open the video. Right? We have to tell the software about some specific dimension. Right? Software doesn't know what is the distance between different points at the beginning. It's just a video. Right? Usually some videos come with some nice frame at the beginning. The first frame tells you all the information about this is the distance, 1 meter. This solid disk is the weight of this disk, or the mass of this is diameter, the thickness. Sometimes it is there. Sometimes I tell you exactly the distance between 2 points, which is the case for the first project. I gave you the distance between 2 points, so you can use that distance for your reference. So first thing, you go to this icon, I would say, to create a calibration stick. I go to new calibration stick. So click on that. Pay attention to guidelines provided by software. Here in this yellow color, it says shift and click to mark end one. So hold down the shift key. Once you do that, you see the mouse pointer changes. So I'll go from the top, this point, end one, right? I want to say this distance is 1. So 1 meter. So I click here, hold down the shift key again, and go all the way to the bottom to mention the second point. Once you do that, you can let the shift key go, and it creates the straight line which measures the distance, and you can put what that distance is. So I know this is 1 meter, so I put 1 amp. Right now the software knows the distance between these 2 points is 1 meter, and it's going to use that for all the measurements when it's running the analysis. The second thing you need to tell the software is where to put the coordinate system, right? And that, the button next to it. I click on that, a coordinate system shows up. You can left click on the origin and move it around. Put it wherever you want. In this case, let's just put it exactly where I put the beginning of this measurement stick. Let it go. When you move it around, you also see that look at these 2 boxes here. They change the the numbers, right? They try to identify where we are in the video or in this frame specifically. So I'll put it here. Now, when you get the coordinate system, the default is x-axis is towards right. You see this small vertical line crossing this axis. This is representing x-axis. And the angle that it has from horizon is represented by 0 degrees here in this box, angle in degrees. So if you want to change this, in this case, I want to change it and I want to make x along the direction of the motion of this yo-yo. If I play the video, you see the yo-yo is going down, right? It goes through the frames, go to the end. You can just take it all the way back to the beginning. Right? These are just the frames. If you want to go frame by frame, you can click on this and it goes frame by frame. Take it all the way back. Since the yo-yo is going down in this direction, I just want to define my x-axis along the direction of the motion. So I'm going to left click on this small horizontal bar and rotate, move this axis or the whole coordinate system, better to say, this way. I move it, try to move it and put it in vertical line. If you can't exactly make it vertical, here you can change the angle manually. Right? If I put minus 90 degrees, it's almost vertical. Probably the video is a little tilted, so sometimes you might end up rotating this, let's say minus 89.5. Right? It's a little tilted to show that, well, the video or the camera was a little tilted. But what I want is the direction of the motion along the line that the yo-yo is moving. So the coordinate, you define the coordinate. Then you have to tell the software where the mass or the point that you want to track is. So to do that, you go to create a new track. You go point mass, pretty much that's all what we use for this course. Mass A shows up. Now follow the guidelines, right? So shift, hold down the shift key and click wherever you want to say the mass is. So I'm going to hold down the shift key, the mouse pointer changes, and click on this. Now once I do that, it automatically goes to the next frame. So I define the mass. Right? If you wanted to do analysis in the software, we could also say how heavy that mass is, but for most of our analysis, we only take the displacement out of this software. We don't do further analysis within the software, which has the capabilities. So just let it as 1 kilogram. We don't even have to modify. If you want, we can just put the value of the mass from the given number, like 491 grams. Right? I'll just leave it as 1 kilogram. Next, you have to track the motion. So go to mass, left click on it. I'll use auto tracker almost always. You can do it manually if you watch those videos, and one of them, the author or the developer of the software goes into details how to do it manually. But Use Auto Tracker, click on that, this window pops up. Now, follow the guidelines, right? Create a new keyframe. How do we do that? Shift, Control, click the video frame of interest. So you hold down Shift key and Control key at the same time, and you see the mouse pointer changes. If I let go these two keys, it's really just a mouse pointer. But if I hold Shift and Control key down, it changes. So it is circular, like a target. And I pointed, I moved so many frames, I can just move one frame. Control and Shift, and I say, well, do you see this point? Try to find a point that is distinguishable from its environment. So I say the software, I tell the software, take this point and left click on it as what I want you to track. I want you to track the motion of this point. Now this area or the box shows up. You can change the size of this box. Sometimes you end up doing that because if it's too small, that is the box the software searches for where this point that is trying to track to find that point in each frame. So if this box is very small and I go to next frame, well, in this case, this motion is very small, but if the box is very small and I go to next frame, that point might be out of this box. So the software cannot find that point in the next frame. So the box should be big enough for the software to be able, it's the search box, keep that in mind, to be able to find the point in every given frame. And at the same time, it shouldn't be too large because then it takes a lot of computation, because that's the box that the software does the video analysis for. So I keep it around this size. If it's not good, you'll see in your analysis, you get an error, so you have to change the size. And then what I do is just I'll go here and say, well, click to start searching. Evolution rate and auto mark, you can take a look. If you stay on it, it gives you some explanation on in this box here, the template, you know, the auto mark level is the minimum match score. There's a good description, explanation about what it is in the software, one of those tutorials. You don't need to be an expert on that, but if you're curious about it, you can look at those tutorials. So I do search. Right? Now what happens is it starts going through all the frames and track that specific point that I'm trying to find its motion. So I got everything properly and everything works fine. Now I can just close this and come here. You see, I got a plot of X versus time. X is whatever the X is along the X axis I defined, and T is the time of the motion. Obviously, this is a falling object. This is a falling object, so the displacement is, if you look at the slope of displacement is a second order function, and the velocity, because the velocity is increasing. Right? And you get the data points here, X, time versus X. Y, we don't care. Well, we are not looking at the direction of the motion in y-axis. But if you click on this X, you can actually look at different things. You can look at the Y position. Right? It's around 0. It oscillates a little bit, but that's not what I want to measure. So just keep it on X. And it tells you the X is measured in meter, time is measured in second. So this is the plot you get. If you want to just export this plot, right, so don't want to go further, right click on here and choose a snapshot. Right. That opens up a new window. You can just play around with the size, you know, what size you want it to be. And then you pretty much go to File, Save As, and save it as usually I save it as PNG file. And that's a figure you can put in your reports. Now, that's not a good way of doing it, though. The other, I'll tell you at the end where to look for actually be able to use the data from this. What I mainly want you to do is that typically export the data from this to graph software and then use that to plot. So you can actually plot your analytical solution along with your data points and compare them, which is going to happen for I believe in first project. And for that, you have to watch the second tutorial I made for graph. Over there, I specifically explained and gave you the procedure. How can you get the data from tracker and import it to graph and plot it there. For graph though, sometimes, well, to export the data, let's see how does that work, or to do further analysis. Right? If you right click on this, the same place you find the snapshot, we can go to analyze. If I click on analyze, it opens up a new window, same data, right? The data is here in the left, 2 columns, time versus X. And the same variables, I can change X and T. The X is versus T. You can flip it by saying T versus X, doesn't matter. Now here, a couple of things. First, you can export the data. Right? I can just export X and T, go to File, go to Export Data, and use Export Data. Let's go to Desktop, go to, if I can find, where did I put, let's say today's class. Just call it output.
Professor, I think you're importing, not exporting.
Am I? Okay, let me do it again. File. Yes, export selected data. Thank you for mentioning that. I was just, so export selected data, thank you. So I selected the data here. I just selected these 2 columns, and I go to File, Export Selected Data, and it's just going to be exported as a text file. It's a typical file. You can get XML. I typically go with text file. And it says Mass A. You can change the name and save it there. Now, if I go to that file and open it, that I just exported, it's pretty much just 2 columns, very simple columns. First column is the time. Tells you it's mass A, first column is time, second column is X. How to take this from here to graph software, watch that second tutorial I made for graph software, and you will see what is the best way to do this. Now, if you go to measure, if you click on coordinates, right, then it gives you capability to just move around on these points and explicitly get the number or coordinates for the point. You see the yellow box there, it tells you the time and value. If you go, let me check that. If you go to slope, click on any line, it gives you the slope of the line at that point, which in this case is velocity. Right? The velocity is increasing, obviously. If you look at the bottom left, you see it says the slope. Uncheck that. The last one is you can just get the area under the curve. Right? For some dynamic analysis, vibration analysis, you might use that. Like the area under the curve for velocity would give you the displacement. Uncheck that. The last thing I want to talk about is shift origin. To talk about this, let me close this, go back to where I was. Let's say after analysis, you want to change where the coordinate system is. Let's see, I want to take this, not this. I want to take this coordinate system. Let me move it around so I have access. I'm going to put this back where it was. You move the coordinate. You decide that, well, go back to the first frame. I want to put the coordinate where the first or initial position is. Right? You can put it here. If you do that, follow what happens on the plot on the right side. Right? You see the range for the X changes when you change the coordinate system, because it measures where the position is with respect to that. So if I just put it somewhere here, let's say, so it's starting from some random point. Now, how can I set it on 0? I want it to be at 0. Let's say I want the coordinate be exactly where the motion starts. In some cases, you will need that when you're looking at a spring mass system later on for projects. So you go to analyze again. Now here you can use shift origin, meaning that you can shift the origin, obviously. If you click on that, now you can shift the origin both based on time and based on displacement. Here you see the initial position is 0.103. I can shift the origin exactly that much, 0.103. We can type there, 0.103. Enter. So it shifts the origin. Now the beginning is 0, very small number, but it's almost 0. So now you can export this data. instead of the previous data. Right? You can export the selected data. This is going to be the data that the origin exactly is at the beginning of the motion. Anything else? I told you pretty much everything that you need to know. The last thing I want to mention is that quickly, so this, as you realize that this tells you what position you're interested, X, Y, Z, rotation, angular velocity, angular displacement. You can even get velocity from here. If you go there and you go to velocity magnitude, so almost increasing with the same slope, which is what we expect, right? This yo-yo is falling down, so the velocity is increasing because acceleration is constant, is acceleration due to gravity. So the velocity is increasing with a constant rate. Now let me open a different video. Let me open this pendulum, which is the video for your first project, actually. First thing I want to mention is that you don't need to start the analysis from the first frame. For instance, in this case, it's much easier if you just keep going and going and get to a point that I let the pendulum go. You see that? This is probably the best place to start the analysis, like here, when I let the pendulum go. I do the same thing I did. I put the calibration stick, hold down the shift key. From here, I told you what this distance is in the project file. I actually don't remember, probably 30 centimeters. I'll just use centimeter, change the unit length. Yes, why not? If you don't want to change the unit length, you can always put 0.3 meter, keep it in meter. Put the coordinates. I'm going to put the coordinate system somewhere that the pendulum is connected, rotate it this way so my X is downward. And let's just keep it minus 89 degrees. Seems like it's aligned with this line. Create a point mass. Where the point mass is, well, hold down the shift, click on the mass. It tells me, it goes to the next frame. Tells me where the mass is. Or I tell the software where the mass is. I'll just go back to the previous frame. Now I want to track it. Go to mass, auto track. As before, I have to create the first frame, shift and control, hold down, come here and click on or around this mass that you want to track. And this time you have to make it probably a little bigger. And then do the search. So, oh, now see that's a good thing. Now you get an error because at this point, this frame we define is not big enough that includes the mass we were looking for. So the software is searching inside this box, but cannot find the mass because it went out of this frame. So what you do is that, well, you expand this and you say search this. Now it can find. Now it continues the search. So keep in mind the optimal size of this box. That box depends on what the motion, how fast the motion is and which direction it's going. So it does the analysis. It follows the pendulum. I can just stop it here and close this. Here gave me X. The X is not what I'm looking for. I'm not looking for the motion along the X axis. I'm looking for the motion along theta. And theta is the angle along, well, theta angle from X. So if I go here, instead of X, I can switch that to rotation angle. That's what I get. Now it looks more like the oscillation I was looking for. Like it's a pendulum swinging back and forth, and this is theta. Now this theta is in degrees. If you don't like seeing it in degrees, you can just go to Edit, Preference. The box shows up, this pops up. You go to, I believe somewhere, maybe if I can find it, that would be great. Okay, so under display, you can change the angle unit, let's say to radians. Right? If I click, go back here, now it's in radians. It's up to you. But the same process, analyze, you know, I do not need X here, so I can just get rid of that. You can just delete the column from there and just get, let me see if I can actually do it. Analyze, get rid of X and point related to X. I actually have to do it separately. Let me see if I can do it here. actually point. See if I can get the table view. Okay, so here you can just delete the value for x and go back to your plot. I can't do it here, but it's just a label. But you can just go back to your plot, and I'm running out of time. And get the plot, go to analyze, export the data for theta, and just get the value for theta. Hopefully this helps you to get started with the project. So use this video, the recorded version of the class, obviously, if you forgot something about how this software works. And I'll send you an announcement telling you about the project, announcing that when I put the project on Moodle, which probably most definitely will be by the end of the day. In that video, in that announcement, I'm speaking so fast. In that announcement, I'll tell you and remind you to take a look at the second tutorial video for the graph software that tells you how to deal with the data that exported right here, how to deal with that and how to import that to graph to get a better plot. Okay, any question, guys, about this?